The second lecture for this week, we're going to start talking about the different types of rocks. There's 3 different families of rocks, which we'll discuss here in a second. So we're done with minerals, and we'll move on to the different families and types of rocks. Just to remind you, we defined in the last lecture that rocks are made of minerals. So minerals are the building blocks of rocks. And if you have something like granite here, you'll have a mixture of a bunch of different minerals that all squish together to give you a solid rock. So there's 3 families of rocks. And again, you might have learned about this at some point in your educational career. So they're not classic rock, punk rock, and hard rock. They are metamorphic, sedimentary, and igneous rocks. So for this lecture, we're just going to talk about igneous rocks. What I will say is that you are already familiar with igneous rocks because we already learned about volcanoes, and volcanic rocks are igneous rocks. So the names and the terms that we'll talk about here in a couple of minutes are ones that you already heard before, assuming you're watching these lectures. All right, so just to show you kind of the origin of rocks, there's basically anywhere on Earth's surface is fair game for where a rock can form. But what this figure is showing you is that you can get igneous rocks, for example, forming at divergent plate boundaries, where you get magma spilling out onto the ocean floor, cooling down into basalt. You can get rocks that form at subduction zones. If you have a trench and you have a convergent boundary where 2 plates are colliding and something's getting subducted and melted, you get igneous rocks that will form there. Anywhere on the ocean floor, you can get sedimentary rock that forms. You can get sedimentary rock that forms in mountains. You can get them in lakes, dunes, deserts, environments. Then you can get metamorphic rocks that form when tectonic plates collide as well. So the point here is that basically anywhere on Earth's surface or at the bottom of the ocean is kind of fair game for a rock to form in some way or another. So let's talk about igneous rocks. That's, again, what we'll focus this entire lecture on, is just igneous rocks. So igneous rocks come from the cooling of melted rock. Melted rock is magma. We already talked about the difference between magma and lava. So if you take lava or magma and it cools down over time, you're going to get a solid rock. That solid rock is an igneous rock. So igneous rocks form from the cooling of a melted rock. You have liquid, magma, or lava. That cools down, forms a solid rock. You get an igneous rock. So here's an example. We have this Pahoehoe lava, this kind of flowy, oozy lava in Hawaii that has spread across the landscape. It cools down. When it cools down, it forms a solid igneous rock, basalt. But if that was underground, it might form something like granite or a rock that we call diorite as well. What you'll notice when I talk about igneous, metamorphic, and sedimentary rocks is that there's all these categories that geologists like to put them into. So for each one, sedimentary will have 3 categories, metamorphic we have 2 categories, and igneous rocks we have 2 categories. So here's your 2 categories of rock, of igneous rock. There's volcanic igneous rocks, which we also call extrusive. So a way to think of extrusive is that it's external to Earth, it's on Earth's surface. So this is anything that comes out of a volcano. The opposite of a volcanic rock is what we call a plutonic rock. Another term that we use for plutonic is called an intrusive rock. The way I remember this is intrusive is internal to Earth, so it is underground. This is magma that never ever erupts out of a volcano. It just gets stuck underground, and over millions of years, it'll turn into a solid igneous rock like granite, as an example. So volcanic erupted on the surface, plutonic cools underground. So when we're looking at igneous rocks, we have a couple ways of classifying them. Again, obviously, if we were physically in the classroom, you'd be using hand samples of these rocks and looking at them and trying to identify them. So I try to get some good pictures here to help you. But if we're looking at igneous rocks, we can classify them or group them into different categories based on their properties. So what I want you to notice is that if you examine these 4 pictures here, all 4 of these are igneous rocks, but based on color, we could group the left 2 together and say that these are light in color, and we could group the right 2 together and say that these are dark in color. So one way that we classify igneous rocks is based on color. Is it light or is it dark? A second way that we can classify igneous rocks is that we can break them into categories based on texture. So the texture means that it would either have very large grains that you can visibly see in that rock with the naked eye, or it could be small grains where you can't actually see any individual minerals or outlines of minerals in that rock. So if you're looking at the two images on the top here, what I see is that in both sides, even though it's a little bit more challenging on the right one because it's darker in color, you can see individual minerals. So you could trace the outlines of the individual grains in each of those two rocks on the top. So we can categorize or lump those together based on their texture, which is large, or what we call coarse grained. The two on the bottom, you can't see any individual minerals. You can't trace any of the edges of the minerals. So these are what we call fine grained or small grained. So they can be lumped together by the fact that you can't actually see any minerals in those rocks. We'll talk about why that's important in a second. So given that, just a hypothetical question. So let's say you have coffee in a mug and you spill that mug over, and then you have coffee in a thermos. So which of those is going to cool faster? And the hot coffee is going to cool down faster in the one on the left here that you've spilled because it gets surface area, it spreads out, it's exposed to the atmosphere, which cools it down. On the right side, in our thermos, for example, it will take the hot coffee a long time to cool down. And the reason is because it's kind of sheltered within the thermos, or in this case, it would be an analogy to being underground. So why I use this example is that if you have lava that spills out onto Earth's surface from a volcano, it's basically like your spilled hot coffee here. It cools down quickly, and you get rocks that don't have time to grow minerals. So they tend to be those fine-grained ones where you can't actually see individual minerals in those rocks. On the right side here, our thermos is supposed to indicate like an underground magma chamber. And this indicates plutonic or intrusive igneous rocks because it has this heat. It's not exposed to the atmosphere, so it takes a much longer time to cool down. And the result of that is that you get these large grained igneous rocks like granite, for example, that form over millions of years as lava or magma cools underground. Okay, so just to kind of put that together in this kind of grainy slide here. So extrusive or volcanic rocks, they come out of a volcano because they're exposed to the atmosphere. They're like your spilled coffee. They cool quickly, and because of that, crystals can't grow in that rock. So they're what we call fine grains. You can't see any individual grains in those rocks that come out of a volcano. If we look at an intrusive or plutonic igneous rock, they're like ones like in this situation here. They're not erupting out of a volcano. They cool down very slowly. They're like your coffee in your thermos. They cool down very slowly over millions of years. So as a result, they're what we call coarse grained, which just means they have large enough grains to see with the naked eye because it has had more time to actually grow those crystals. So let's talk about some names. As I said, some of these names should already be familiar to you because we talked about them in the volcanoes lecture last week. There's rhyolite and andesite and basalt are the three that we've already covered. And then there's granite, diorite, and gabbro. So let me walk you through how I have this broken down. I have plutonic, so these are the ones that formed underground. Those are these three on the top. I have volcanic, these are ones that come out of a volcano on the bottom. Those three on the bottom. The ones on the top, since they cooled underground, they have time to grow crystals, so all of these are considered coarse-grained, meaning you can see the individual minerals in granite, in what we call diorite, and in what we call gabbro. Volcanic cools down quickly, so you get small crystals or small grain sizes, so rhyolite, andesite, and basalt, you can't really see individual minerals in those rocks because they cooled too quickly. Another way this is arranged is that high silicon and oxygen tends to give rocks a lighter color. So it might either be white, pink, or tan, like granite and rhyolite. These are lighter in color. The darker ones in color are on the right side, like gabbro and basalt. And the reason for that is because they have low silicon and oxygen, which makes them darker in color. So granite and rhyolite, high silicon, lighter in color. Gabbro and basalt, low silicon, darker in color. The only other thing I want to point out is that granite and rhyolite have the same exact minerals in it. The only difference is just that they're bigger in granite because they had more time to grow. They're smaller in rhyolite because they had less time to grow. Same thing with gabbro and basalt. You would find the same exact chemistry, the same exact chemical makeup and minerals in gabbro and basalt. The only difference is that they're bigger in gabbro because it formed underground, and they're smaller in basalt because it cooled above ground. Just to remind you and to bring it back to volcanoes, if we're talking about rhyolite, tan, high silica, super explosive type magma or lava, So that's something that would come from a supervolcano like Yellowstone. Just to recap, if we're talking about andesite, andesite cooled from a stratovolcano. Andesite is a mixture of basically continental crust mixed with ocean crust at a subduction zone, which is where you get stratovolcanoes. So you get this gray kind of mixture of light and dark, you get gray. And then you get your stratovolcano is the type of volcano this would form from. So you have Mount Rainier in the image on the bottom right. Lastly, basalt. Basalt comes from places like Iceland or Hawaii, where you have lava just kind of oozing out of the surface. It's dark in color. It can flow pretty far due to low viscosity. So basalt is cooled from lava, usually from a shield volcano, like the one on Mars, Olympus Mons that I talked about. Okay, so that's kind of the external or looking at extrusive volcanic igneous rocks. What I want to point out is that there are large regions across the US where we have intrusive igneous rocks like granite that formed underground in a cooled magma chamber over millions of years, but they are now exposed on Earth's surface. An excellent example of this is Yosemite National Park in California. I hope that some of you have been there, but if you haven't been there, I hope you get to go there one day because it's beautiful. And it's a glacial carved valley in California, but all of these peaks that you see here, the reason they're light in color is because they're all granite. This is Half Dome, so a famous feature here. You can hike up it if you're so inclined, and then look out kind of over Yosemite Valley with its light colored granite. So how does something like granite become exposed at Earth's surface? What this animation is showing you is kind of what happens or what happened in Yosemite in the past. So there used to be volcanoes. Those volcanoes used to be active, but then it kind of lost its energy source and you have this big pool of magma underground. It cools down over millions of years into a granite, a intrusive underground igneous rock that has large crystals forming over that long of time. So to get that exposed at the surface, what has to happen is that volcano loses its heat source, it cools down, forms solid granite, it erodes away. So all of the layers that used to be on top of that magma chamber erode away. And now the end result is you get something like Yosemite, like this picture here, exposed on the surface. One quick slide just to mention other types of igneous rocks. So we didn't cover all of them. There's more. There's something called volcanic tuff. So that's just kind of a gray, cindery type rock that's just made from solidified ash. So if you have a particular volcano that erupts a lot of ash and it forms a solid rock, you can get something called tuff. Obsidian you might have heard about before. Obsidian is volcanic glass. So basically a volcano erupts and the lava cools so quickly that it doesn't have time to form any mineral grains. So you get volcanic glass instead. That would be obsidian. And if you have a lava that erupts and cools so quickly, but it's full of a lot of gas bubbles, instead of forming obsidian, which is the dark volcanic glass, you get pumice, which is a more frothy volcanic glass. So pumice, if you've seen pumice or used it for exfoliation or anything like that, it's basically less dense than water. So if you have a pumice stone, it'll float on water. And the reason is because it has all these bubbles in it from when this lava exploded out of the volcano, and those bubbles cooled in that blob of lava that cooled really fast. All right, so I just want to finish up with some kind of the usefulness for igneous rocks. So granite is useful. Bunker Hill Monument in Boston, Bunker Hill Monument in Boston is made from granite. Granite is a common building material, countertops, headstones. If you want a headstone, I know it's a little bit morbid, but if you want a headstone that lasts a long time, granite is really resistant to erosion. So granite makes a good headstone for that reason, because it doesn't break down. And then lastly, Mount Rushmore basically is just carved into granite in South Dakota. If we flip over to basalt, so if we look at uses for basalt, what's called ballast rock in railroad tracks, that's usually basalt. So this kind of loose rock here that holds the railroad ties or the railroad tracks together, that's usually made of basalt. The Easter Island heads were carved into basalt. It's another common building material or landscaping materials, pavers, walkways, tile can be made from basalt. And then roads and asphalt. So if you are out walking on a road, you're interacting with basalt, or driving on a road, that makes more sense. You're driving on basalt. So basalt is kind of mixed in with tar and other materials to create asphalt. Okay, So at this point, you should be able to take the Igneous Rocks quiz on Blackboard. And then the table that I have in here is just to kind of help you out with the final question on the quiz. So if it makes more sense to you to look at it in this kind of form here, feel free to pause this and keep it open so you can answer that final quiz question. And then in addition to this, there's the Rocks homework that's also in the week 3 folder. You should be able to complete question 1 on the Rocks homework now after watching this lecture.